All right. So, what we're going to do today is we are going to discuss the past paper questions from electric fields. Let's focus on the most recent questions first. Let's see how far we can go. The first question comes from year 2021, the latest MCQ, 17th. 2-point charges plus 4q and minus 4q are fixed at distance x apart as shown in the figure. Another point charge plus q does not experience a net electric force when it is kept along the same line at distance y from minus q. The relation between x and y is given by okay, so first it's better if you try this question and then you watch it, then only you will be able to realize where you go wrong. Let's read the question. 2-point charges of plus q, here we go, plus 4q, sorry, minus q are there. Another point charge plus q does not experience a net electric force. So normally when they give questions like that, the middle one doesn't experience a force. But in this particular question, they are saying plus q does not experience a net electric force. Right, so I'm going to use red color for plus 4q. Okay, and I'm going to go with green color for minus q. We all know plus 4q will repel plus q because similar charges repel each other, and plus q will give the same force on plus 4q. If you want, you can mark it, there's no harm in it, but that is really irrelevant for this question. And minus q, what does minus q do? When you have minus q and plus q, they will attract each other. So minus q will give a force towards left side on plus q will give a force to minus q on the towards right side, F2, and these two will also attract each other, but that is not our concern in this question. Our concern is only this plus q, because they are saying plus q does not experience a net force. If that's the case, what I've underlined in green color, so I can say what F1 is equal to F2. F1 is the force between plus q and plus 4q. F2 is the force between minus q and plus q. F1 is, now for force, what is the equation? Electrostatic force according to Coulomb's law, it is equal to Q1 Q2 over 4 pi epsilon naught r squared. That is when there are two charges, Q1 Q2, regardless of their sign. Now you don't substitute sign here, you don't substitute negative and negative values here, you substitute only positive value to find the magnitude of the force. If both are similar charges, you mark the forces away from each other. If both are opposite charges, you mark the forces towards each other. That's it. Okay, so if you take F1 is the force between plus q and plus q, plus 4q and plus q. So for F1 I have to write Q1 Q2. Q1 is 4q, Q2 is q divided by 4 pi epsilon naught. The distance between those two charges is x plus y, careful, x plus y squared, and then equal to F2. What about F2? F2 is equal to the force between q and q. I'm not putting minus q here because using that plus minus signs I have considered the direction. So here you have to substitute only the magnitude. 4 pi epsilon naught into the distance between those two charges is y, so it's y squared. Right, well, few things can be cancelled out here. As you can see, 4 pi epsilon naught gone, 4 pi epsilon naught gone, and here you will have 4q squared. So this q and with these q's can be cancelled out, which will leave just 1 on top and 4 here. If you do some cross multiplication, what will happen? If I take this y squared up, I'm getting 4y squared equals x plus y whole thing squared. Let's take square root on either side. It will give us 2y on left side, x plus y on right side, and therefore 2y minus y is equal to x. Surprisingly, y is equal to x, and the correct answer is the first one. How many of you got this answer? Can I see a raise of hands? Right, good. Now the question is, first question should have been, how many of you tried these questions? You should have tried these questions because we have covered all the theory so far, right? And you should be able to do this, right? Look, this is 2021, so read the question twice. Normally we consider the equilibrium of the charge in the middle, but this time they have specifically told consider the equilibrium of the charge in the corner. You have to be extra careful. right? All right. Right, we'll move on to the next question now. That is this one. I think we tried this question at the class, yeah, didn't we? We already tried this question at the class. Yeah, but give me a minute. I'll just quickly explain it one more time, very quickly. See if you still can remember it. Okay. So this is a question from 21, once again, 45th MCQ. A solid conducting sphere of radius 2r contains a cavity of radius r inside it, as shown in the figure. Okay, there's a cavity 2r. The sphere carries a net charge. So this is a conducting sphere, a solid conducting sphere. When you say a solid conducting sphere, this is metal. Inside the metal, electric field lines will not travel through metals. So there can't be an electric field intensity from R to 2R. That's why in all the answers, that part is 0. So they have taken the fun out of it. But anyways, they have made the choices difficult for you, right? Because if they have given an answer where from R to R E is not 0, you could have easily eliminated, but you can't eliminate anything here. Good. Another point charge of plus q is placed at the center of the sphere. So you see a plus q charge here. Which of the following graphs best represent the variation of the electric field intensity E with the radial distance r from the center of the sphere? So the r we have to consider is from the center of the sphere, and you should go out like this. Sorry about that. You should go out like this. This is the r they're talking about. Right. Okay. So when r from 0 to capital R, this is in this region. In this region, if you see, this is where simple r is between 0 to capital R, right? So then you just focus on region by region. First of all, you take that region. In that region, you have a point charge in the middle, right? Point charge in the middle. Don't think of outside and all. Just focus on the inside area. Your point charge in the middle, and whenever you have a point charge, around a point charge, if you take a plus q charge, and from that point charge at a certain distance, if you talk about electric field intensity E, that is given by q over 4 pi epsilon naught r squared. That means E is inversely proportional to r squared inside the sphere, in the cavity. So in the cavity, the variation of E with r has to look like this. From infinity, it will come down. When I say from infinity, it's a large value. So your graph cannot start from a fixed value point. See these graphs? No, none of these graphs start from y-axis. They start slightly away from y-axis. The reason is that this inside the cavity, this is the equation. So it should come up to there, and just inside the shell, at this point, just inside the shell here. It's very important. Just inside the shell, what is the distance to that point? Capital R. So just inside the shell, where I have marked in red color dot, in that point, at that point, the E value, it's going to be equal to what? It's capital R distance away from the point charge. So it's q over 4 pi epsilon naught r squared. So it will reduce and come to a certain value. It will not go to 0. It is not 0 there, because if you take this point and if you draw a sphere there, inside that sphere there is a charge. So E can't be 0 here. There will be electric field lines. Therefore, we can eliminate few answers now. This is definitely wrong. This is wrong. Because this starts from 0 and increases, and this is wrong because it goes up to 0. It is not 0. It will have a fixed value. And moreover, we know whenever you have a charge inside like this, plus q, on the internal surface of the sphere, a negative q charge will be induced. I mean, when you have a positive q charge inside, a negative q number of electrons, negative q charge, electrons of negative q charge will get attracted towards the inner plate. So plus q here, negative q here, and because of that, another positive q will be induced on the outer surface. Already there's a positive q, another positive Q will be induced on the outer surface. So your sphere will actually look like this. Your sphere, if you draw the net charges in the sphere, it will look like this. How? It's going to look like this. Right, let me just mark the charges pretty quickly. There is a charge in the middle, that is plus Q. And there will be a charge of minus Q in the inner surface, on the inner surface. I'll just mark it this way. I'll just put some minus signs here, minus, yeah, because the inner surface will be negatively charged, and that is minus Q. And the outer surface will be, people, positively charged, and that will be 2Q. Why 2Q? Already a Q is there, and the induced charge minus Q, I have plus Q, I have marked in green color, will also be there. So this is how our sphere will actually look like. And we all know when you go away from the sphere, from outer surface, E is going to definitely reduce. You know, all the answers, it's like that. But very important point, what is the electric field intensity just outside the sphere? What is the electric field intensity just outside the sphere? Because we have to compare that with this value. That is going to be 2Q divided by 4 pi epsilon naught 2R squared. Very important. And if you simplify that, what is the value? I'll leave 4 pi epsilon naught as it is, 2Q over 4R squared. So 2 and 4, if you simplify, it's half. So it's half into Q over 4 pi epsilon naught R squared. That means it's half of the value of the internal surface. It will be half of the value of the internal surface. So which one do you think is the best option, guys? Here it is wrong, because look at the values. Here it looks like they both are equal, Bharati. Because if this value is simple Q over 4 pi epsilon naught R squared, they are saying outside the sphere also it's the same value. That we can't agree with, no? And if you take this one, here this looks reasonable. I think this looks reasonable, right? Yes, I think this looks half, because from your eye level you can make that estimation, 4 pi epsilon naught R squared, and here it is half into Q over 4 pi epsilon naught. So I think the best answer for this question will be, the most appropriate one will be the second. Well, we have already done this at the class, but I'm just trying to redo it, because it's after a long break, they have given a question based on the variation of electric field intensity around charged spheres. All right, so this is how you do it. And here we have a point charge inside. Take that into consideration and consider that first region separately, and then go into spheres. And whenever there are metals, there will E will be 0 there, no E. Right, then, so that question is done. Second one from 2021, right? So if you have if you need to watch it again, you can just always read what do you call that, rewatch the YouTube tutorial, sorry. And then we have 2020. Once again, this question is also based on Coulomb's law, but you have to think a little bit extra here. Let's see how do we do this. 3 small conducting spheres carrying plus Q, minus Q, and plus Q are located. Charges plus Q minus Q are located at the vertices of an equilateral triangle ABC situated on a frictionless horizontal surface as shown in the figure. Spheres at B and C are fixed. All right, spheres at B and C are fixed, so they will not be moving even though a force is acting. Let's say they are like fixed with nails or something, so they are not moving. But this is free to move, right? Yeah, A is free to move. The possible path of sphere A is best represented by, right? Before I explain the question, can I know a few things? Number one, am I audible enough? I'm not talking very loud because I have a really bad throat fever. I couldn't even speak for 2 days, so I just want to know that am I audible enough, because I'm not talking very loud. Yeah, okay, good, thank you. Now tell me, if you tried this question, what was the answer? Okay, after thinks it's B. I'm now student thinks it's C. Okay, Rushma also thinks it's C. Deepak thinks it's E. So yeah, variety of answers. Some of you think it's A, some of you think it's C, some of you think it's E. It's a very interesting question. You need to think a little broader. So what you have to do is I'm going to draw a few diagrams and I'm going to consider situations like the beginning and after the charge moves a little, what will happen likewise, right? I think that will give you a proper idea about this. So let me consider around three situations, one after the other. Okay, in the timeline, one after the other. So this is these are three different times. Let's say there's a camera fixed, and we are taking pictures after three different situations. So first of all, let me quickly put some lines here and make broken lines. Right, sorry. Right, this is okay, manageable. First of all, people, the charge plus Q is here. Okay, and these two fixed charges, they are minus Q, minus Q and the other plus Q. So you see, I'm using a color, specific color for this charge. That means I'm going to use the same color to mark the forces, right? Right. Yeah, I'm going to use red color for this plus Q. Right, so let me quickly put that here, because this plus Q in red color and minus Q in blue color, they are not going anywhere because they are fixed, aren't they? Now let's mark the, initially we know this plus Q will repel it. Yeah, plus Q will repel it in this direction, force F will act, and minus Q will attract it, same force. Why is that? Same charges, same distance. It's an equilateral triangle, isn't it? Equilateral triangle, see? So this will experience same force. That's why I have marked F and F. And we know when you have two forces like that, the resultant is in this direction. Correct? This is the resultant direction, resultant force. Therefore, your charge will move. At the beginning, it will move towards left. Now, after says answer is B. After, I don't know, someone said answer is B. So that's what it says. But the problem is they are asking for the subsequent path. Let's move that charge a little towards that side and see what's going to happen after that. You have to be a little careful. Let's say it has slightly moved like this. Who? The plus Q charge. Now there is a small issue, people. What is that issue? The distance to that charge from plus Q is greater than the distance to that charge from minus Q. Do you agree with me? Correct? It has slightly moved now, right? Slightly moved. Give me a second. Slightly moved, and but the problem is this: they are not. The charge will not be at the same distance from the blue color and red color. What do you call that? Charges. And to make you understand it more, put this as R1, and I'll put this as R2. Okay, who is bigger, R1 or R2? Hurry up. Who is bigger, R1 or R2? Obviously, you should be able to recognize R1 is smaller than R2. Therefore, the force given by the minus Q charge will be larger. So we draw a larger arrow here, F1. Okay, and the force given by plus Q charge will be relatively small, F2. And in mechanics, we have learned how to find the resultant of two forces like this. How do you do it? We complete a parallelogram and we draw the force. Now look at what's happening. Resultant force, it is in this direction, isn't it? Resultant force is in this direction. Resultant force. So your charge will not, the plus q charge will not go straight, because the direction of force keeps changing. So it was started straight, now it has been slightly downwards, right? That means it should go somewhere here now, no? It can't go straight, it should go somewhere here. And now once again, if you notice it carefully, the length from blue charge, it's even smaller than the previous scenario, right? It's even smaller than the previous scenario. Now it will be even more dominant. Where the attractive force will be even larger, and the repulsive force will be even smaller, right? And now when you find the resultant, it will be even more downwards, correct? Therefore, how do you think your charge is going to go? What is the best path? So the path is going to be like this. It started flat, and then it bent down a little, right? It's going to bend down a little, and then it's going to bend down even more, like this. Therefore, when you connect all the dots, you will be getting a path which looks like this. So guys, tell me which one is the best answer. C, right? C is going to be the best one. So you have to do some following up here, because instinctively you might go with answer A if you consider only the initial point. You can't do that. It's a tricky question, so be careful, because the force and direction and the magnitude of force keeps changing with time, right? Fine. It somehow I don't think it's a circular motion. Circular motion means you should have a constant force towards the center, right? This force is not going to be constant. It's going to keep changing. So I don't think it's a circular path, it's a curved path, not a circular motion. Right, good. So that's done. The modern questions are really interesting. How you knew path of A? How you knew path, whether it's straight or curve? No, I mean just consider the forces. Earlier the force is flat, the horizontal, then it's slightly bending down, then it's slightly bending even further down. Then I just marked each instance here. This is one instant. Okay, I'll mark that in green itself. So initially the force is like this. I mean, initially your charge is pulled this way, right? After that it's pulled this way. After that it's pulled this way. Now connect everything. Then you get that curve, don't you? That's how I said it's curve. It can't be a straight line. There's no straight line answer. Oh no, straight line means it should have been like this. Everything should have been like this. Then only it will be straight line. All the small arrows I drew should have been along this. Then only it will be a straight line. When you keep on bending them slightly downwards, then when you connect all the dots, it will be a curve. Right. Moving on. Somehow I hope that's clear. For you to get answer as D, all the arrows we draw in broken line should have been straight lines. Why did you mark A? Because A is initially A is pulled right, left side, and then it's pulled down, so it won't go. Just keep going straight, no? It won't keep going straight. It'll move a little to the left, and then it'll go down. Then it'll go down because they keep pulling it downwards. So as the direction of force changes, the path of A will also change according to the force. Okay, right. So that's sorted out. Good. If you have doubts, please clarify like that. Okay, well then we are moving on to the 40th MCQ from year 20. An infinitely long thin straight wire which is located on the axis, on the z-axis, has a linear charge density of minus lambda. Linear charge density. Hope you guys can remember. We learned about this when we learned about electric field intensity around different charged objects. So linear charge density. What is the meaning of linear charge density? Linear charge density is charge per unit length. So you have to divide charge by length. So minus lambda is equal to Q over L. Total charge over, and that is what minus lambda is. Right, so instead of, if you need charge, you can say minus lambda L. But the problem is they are saying it's infinitely long thin wire, so it's very long. A small positive charge plus q of mass m is allowed to move in the xy plane in a circular path of radius r above the wire. Periodic time of the charge is given by, right. So let's put this into a perspective. You have a infinitely long wire. What do you mean by infinitely long wire? It's going to be like this. Infinitely long. Sorry. And around that, now what we're going to do is what do you call that? A point charge is going to perform circular motion around that, like this, in a circular path. Point charge is going to perform circular motion. So this is that path. So let me make it broken lines. It's going to rotate along this path. We all know from mechanics that when we want an object to perform circular motion, what is the main condition, people? It should have a centripetal force. It should have a centripetal force. So when you have a positive q charge like this, whenever it revolves around this charged wire, this is the charge wire is negatively charged. Remember, the wire is negatively charged. So whenever it revolves around that wire, it will experience what? An attractive force towards the wire. It will be experiencing continuous attractive force towards the wire. Okay, so that will be its centripetal force. There will be a centripetal force, and what is that centripetal force? That is the electrostatic force. Centripetal force, it's going to be the electrostatic force, and we just discussed a little while ago. It has a linear charge density of minus lambda, and this is minus, this is plus, so that's why it's experiencing that attractive force. Periodic time. What is a periodic time, people? A periodic time means the time taken for one complete revolution. Time taken for one complete revolution. What is the equation for that? What is the equation for capital T? Equation for capital T is simple. That is, capital T is equal to 2 pi total for during one complete rotation. Time is equal to angular displacement over angular velocity in Weber. For time, when you put capital T, during one complete rotation, theta is 2 pi divided by omega. So instead of omega, you can use the equation 2 pi over capital T, because we will be using omega in the centripetal force equation. So let's try to write the equation. Centripetal force, that is equal to electrostatic force. What is the equation for centripetal force? mr omega square. Here, because I can't use mv squared r, because I had to introduce capital T. mr omega square. F is Fe, right. Fe is going to be, wait a minute, charge 1, charge 2. So the total charge here, we'll take it as, wait a minute, minus q for the time being, minus q. Middle. Yeah, Fe, sorry, Fe is going to be, not capital, I can't put capital Q now, I'll just put, because capital Q means wrong. Let's put it as simple Q. This also will change to simple Q, otherwise it will be confusing. Already they have given a capital Q for us. Yeah. So Fe is going to be equal to simple Q, capital Q over 4 pi epsilon naught r squared. 4 pi epsilon naught r squared. So we need an equation for omega. And the radius of this path is given as r, isn't it? Yes. Yeah. We need to introduce t squared. So if I bring t squared in here, mr into omega squared is going to be mr into omega squared. Now omega is 2 pi over t. Now omega squared is going to be 4 pi squared over t squared. 4 pi squared over t squared, right? So if I substitute that here, 4 pi squared over t squared equal to q, capital Q over 4 pi epsilon naught r squared. I'm making a big mess now here. Sorry. I think I didn't read the question properly. A small positive charge plus simple cube of mass m. Gosh. Sorry. Plus q is on the circular path. That is the one who is performing circular path. So I'll take the capital Q as the charge in this thing. The wire is infinitely long. That has something. Q. Yeah. I think this approach might backfire. So we'll try to do it this way. I'll do it this way. Wait a minute. And we know now, when instead of electrostatic force, we can use this equation. What is the equation? Charge into electric field intensity. Charge into electric field intensity. We have learned in our physics theory, whenever you have a charged wire, from that wire, let's say this is charged, lambda plus or minus, it doesn't matter, lambda is the linear density, and from that wire at a distance of r, okay, tell me what is the equation for E? Is given by lambda over 2 pi epsilon naught r, isn't it? Lambda over 2 pi epsilon naught r. So that is how you have to approach it. Otherwise you can't substitute a value for the charge from here. It is not a point charge. So due to this wire, there's going to be an electric field intensity at this point. I'll take it as E. See, I'm marking in black color because the wire is considered in black color, right? So there will be an electric field intensity, and the equation for that electric field intensity is this: lambda over 2 pi epsilon naught r. So we have studied that, and if you can remember that equation, it will be very beneficial for you. This, all right? So now we make t square the subject. That's it. So t squared goes up, and the rest go the other side. What do I get here? 4 into 2, it's 8. Pi square into pi, it is pi cube. R square is there, m is there, epsilon naught is there. R squared, yes, r squared, r into r squared, and at the bottom q over lambda. Therefore the final answer is t equals square root of 8 pi cube r squared m epsilon naught over q over lambda, q lambda, sorry. What is the answer then, people? First one looks okay, right? First one, yes, first one is the answer, right? First one, right? Can someone check the scheme, if you have the scheme, 2020 scheme, and the 40th one, if you don't mind? And if you have forgotten this, I say, luckily I can remember this. If you have forgotten this, then you have no other option but to derive that equation very quickly. And how do you do that? Right, so that's why you need the basics correct properly. Whenever you have a charged objects, you need to draw a Gaussian surface to cover that object. So to cover a wire, the Gaussian surface you're going to draw is going to be a cylinder. Gaussian surface you're going to draw is going to be a cylinder. Right, so according to the scheme, the answer is first apparently. So we have done it right. And whenever you have we know E has two equations. E is equal to what? No, phi. Phi is our electric flux. Electric flux is equal to, according to Gaussian's theorem, Gauss theorem, it's Q over epsilon naught. And also it has another definition, that is EA. So based on that, we get an equation for E, that is Q over A epsilon naught. So E is equal to, for Q you can put if you take the length of this wire as L, all right, Q is going to be lambda L, because lambda is the linear charge density. I have written here linear charge density. So linear charge density multiplied by length will give you Q, and A is the surface area of the curved part of a cylinder. Surface area of curved part of cylinder, which is 2 pi RL. You must have learned this in O level, into epsilon naught. So what will happen? L and L will get cancelled off from top and bottom. Therefore, you will end up in this. If you cannot remember it, you should have the confidence of deriving the equation the way I just did. But if you can remember, that is going to save you a hell lot of time. See? But even if you can't remember, you should have the confidence, yeah, I can remember it. Because they ask you to derive this in the exams, in essay questions and all. Right, people? So I think this is the only way, people. Sorry, I missed it. In the beginning itself, I should have directed you in that direction. But anyways, sometimes this is what happens when you do questions. You try a method, doesn't work, then you change the path. All right. Even if that doesn't work, you leave the question and go to the next one. Fine. Okay. So the answer is first one. And whenever you see a charged wire hereafter in future, whenever they say a charged wire with linear density, charge density, always go to this and then quickly plug it here. Right. Good one. Take a screenshot and we'll move on to the next. Okay, right. Next one is from 2019. Let's quickly discuss that. The magnitude and the direction of the electric field at point A due to point charge distribution shown in the figure are. Right, interesting. We need to find out the direction of point A, the resultant magnitude of resultant electric field intensity. All right, Weber, can you see the screen now? Is it visible? I think I lost my connection. Right, sorry. Was it lagging when I was explaining? Right, okay, wait, let me quickly prepare it. So we were allocating colors for the specific charges. We are supposed to find the resultant electric field intensity at point A. Point A is in the middle, as you can see, right? So I was quickly specifying, giving colors for each of those charges to mark the electric field intensity resulted by this charge at point A. So purple, let's leave it as black, and then let's give red for this one, and let's give pink for this one, and let's give orange for this one, let's give green for this one, let's give blue for this one, and I have one more, and I'll go with maroon color for that one, maroon color. Okay people, this is black, this is black. So from the purple charge, this one and this one, they are the same distance. It will be the same electric field intensity, right? Why is that? Both are plus q, and both are at the same distance, and that distance is going to be a. This is going to be root 2a, this distance. So if I take this as e1, this is going to be e1, and we know when e is a vector, so this e1 and this e1 will cancel out each other. Got it? Sorry. Correct. What I did was correct, because when you mark electric field intensity, it should be marked away from the positive charge towards the negative charge. Away from the positive charge, away from the negative charge. Okay, and same thing is going to happen here as well, because look at the charge now. Charge is plus 3q, so away from plus 3q there will be a relatively a large electric field intensity, E2 in pink color, because that is resulted by the pink color plus 3q charge, and the same electric field intensity will be resulted at point A because of the orange 3q charge. Why is that? Both are at distance A, and both are 3 plus 3q charges. Later we'll write the magnitudes also. Later we'll write the magnitudes. Okay, so they also get cancelled out, people. Same thing will happen with the red and green one, because the red and green one are going to be E1 and E1. Do you agree? Again, E1. Why is that? Because both are plus q charges, just like the purple one and maroon one, and both are at a distance of root 2a. So that is also done. Now these two cancels out each other, these two cancel out each other, these two cancel out each other. Only ones which are left are plus q and minus q, black and blue. Problem, both of them will create an electric field intensity in the same direction, that is in this direction. Black will create an electric field intensity in this direction. Blue will also create an electric field intensity in the same direction. I'll mark them like this. I hope you can understand what's going on here. And we'll take it as E3, right? E3. The black one is also E3. Give me a second. The red one is kind of, yeah, taking up the space. E1. This is E3. So E3 and E3 are in the same direction, because electric field intensity should be marked when you take a point charge like this. Positive q charge means at a distance r, you will mark E this way. E is equal to q over 4 pi epsilon naught r squared. And if it had been a negative charge at a distance of r, you should mark the electric field intensity towards the charge E, and that will be equal to q over 4 pi epsilon naught r squared. Understood? So that's how it works. Therefore, E1 cancels out each other, E1 cancels out each other, E2 cancels out each other. Resultant electric field intensity is going to be 2E3 now, people. Direction is also important, very important. Resultant electric field intensity will be, there is one E3 towards right and another E3 towards right, isn't it? So one E3 towards right, that is simple q over 4 pi epsilon naught r square, a squared, because this gap is a, plus the other one is also same. Using the direction of the resultant electric field intensity, we can cancel out few. Oh wait, there's only one answer, na? With direction itself we can decide, people. There's only one answer, first one. You don't have to waste your time writing all this. So it's 2q over 4 pi epsilon naught a squared. They have not simplified it, they have just left it the way it is. Yeah, so good. And in case in future, if you need the values, so the other E values, Tell me what is E1? Hurry up. Anyone? What is E1? The magnitude of E1. Magnitude of E1 is going to be charge divided by 4 pi epsilon naught r squared. So r, people, it is root 2a squared. Why is it root 2? Because you have a perpendicular to each other, means this distance is root 2a according to Pythagoras theorem. That's what I've put here. So that is the value of E1. So that is going to be, if you need it in future, just in case, q over 8 pi epsilon naught a squared. And what is the magnitude of E2? E2 is going to be simple, 3q divided by 4 pi epsilon naught a squared. You don't need these things. We are done with the question. I'm just giving you the magnitudes. Right? Please don't forget electric field intensity is a vector. So we have to consider like this. You don't have to mark all these things. You don't have to take color pens and all. I'm marking that to explain. You just can do it in your head. May I cancel out? May I cancel out? Just put a cross, done. Very easy, this question. Okay? Right. For the sake of explanation, I just used all these colors. But when you do the exam, what will you see? Okay, because of this plus q, there's a electric field intensity like this. They will cancel out each other. These two will cancel out each other. These two will cancel out each other. These two won't. Carefully mark the directions. Done. So that's the end of 2019. Now we are moving on to 2019, but a question in the old syllabus. Let's quickly focus on this. Two objects of masses m1 and m2, where m1 is bigger than m2, having charges plus q1 plus q2 respectively, are suspended by two light strings. At equilibrium, objects are in the same horizontal line as shown in the figure. Which of the following choices is true for the equilibrium of the system? Right. Good. So as usual, let's go for two different colors for the two scenarios. We have how many forces will be acting here, people? I think they both are like, they are positive charges, right? So they are positive charges. That means on each charge, how many forces will be acting on each charge? There will be 3 forces acting on each charge. Agreed? 3 forces. One is the weight, so that's going to be m1g, and the other one is the repulsive electrostatic force, fe. I'll put it fe, and the tension T1, right? So I'll write it a little bigger. I'll get rid of the information they have given here and mark it a little bigger. It's going to be T1 here. Okay, right. And if this is theta 1, it should be theta 1 because alternate angle theta 1. And here let's go with blue color for the forces acting on this charge. m2g will be acting downwards, tension will be acting this way, and tension, and there's going to be an angle. What is this angle? Theta 2. So we have to compare T1, T2 and all those things. And don't forget, the electrostatic force will be equal in magnitude. Both of them will be experiencing the same force, Newton's third law. M1 will give a force to M2. If M1 is giving a force to M2, M2 will give the same force in the opposite direction on M1. Right, so what's the plan here? M1 is bigger than M2. So M1G is going to be bigger than M2G. What is the plan here, people? First of all, let's consider the equilibrium here. Upward force should be equal to downward force. So T1 cos theta 1 should be equal to M1G. And if you take the horizontal force, Fe, that's equal to T1 sin theta 1. And here if you consider, upward force is equal to downward force. Upward force is T2 cos theta 2 and downward force is M2G. And if you take the force on this side equal to force on this side, Fe is equal to T2 cos theta sin theta 2, sorry. Right. What's the plan here? Now there are 4 equations we are getting, right? 1, 2, 3 and 4. So as you can notice, 2 and 4 are equal. That means t1 sine theta 1 should be equal to t2 sine theta 2. Alright, and I think instead of t1 we can write an equation from this. Now we will t1, we can get rid of that now. What is it? m1g over cos theta 1. From this you can say t2 . So let's try to figure out, let's try to substitute that there, because having both t1 and theta, it's not going to help us. We need to get rid of one of them. So I'll get rid of theta first, sorry, t1 first. m1g okay, then tell me what can we do? Cancel out g and g. What is sine theta 1 over cos theta 1, people? Hurry up. What is sine theta 1 over cos theta 1? Anyone? What is sine theta 1 over cos theta 1? It is tan theta 1, right? Tan theta 1. So m1 tan theta 1 equals sine theta 2 over cos theta 2 is tan theta 2. Now we are in the right track. I'll tell you why. I'll take both the masses to one side. m1 over m2, it's equal to tan theta 1 over tan theta 2. Okay, but the question, they have clearly told something. What is it? But m1 is bigger than m2 according to the question. So what can I say? Tan theta 1 should be bigger than tan theta 2. So theta 1 is bigger than theta 2. Understood? That is how you do the comparison. Theta 1 is bigger than theta 2 because m1 is bigger than, so m1 is...
Excuse me, sir. Tan theta 2 divided by tan theta 1, it should be, no?
Yeah. Thank you. Yes. Right. Should be tan theta 2, right? Yeah, sorry. Theta 2 here, theta, yeah. Excellent. Yeah, thank you for clarifying that. So it should be tan theta 2 here, tan theta 1 here. Therefore, it should be the other way around. Theta 2 must be bigger than theta 1. Awesome. Right. There are how many answers? Yeah, there are 2 such answers. You can cancel out the first one because this is wrong. This is wrong because this is wrong. This one is also wrong because this is wrong. Theta 2 must be bigger than theta 1. Now we have to compare tensions. Now we'll go to the equations of tension. Now T1, tension, common equation for tension, people. Common equation for tension is this now. T equals, see in this, in the wait. Tension, within tension. Now, no, don't go there. Don't go here because m1, theta 1, everything is involved. Now go to this one. Okay. Now we know T2, T1 sine theta 1. Okay. T1 sine theta 1 is equal to T2 sine theta 2. So if I make this the subject, T1 over T2, just like the previous one, careful. Let's not repeat the same mistake. Sine theta 2 over sine theta 1. Okay. But we just figured out something. What is it? But who is bigger than who? Theta 1 is smaller than theta 2. Theta 2 is bigger. That means sine theta 1 is smaller than sine theta 2. Correct? So what is the final verdict, people? Who is larger? Is it T1 or T2? T1 must be bigger than T2 because T1 is in the numerator, T2 is in the denominator. So the answer for this question is third one. Can I see raise of hands if you understood this? If they had given M and M are equal, T1, T2 equal, theta 1, theta 2 equal, no need to worry at all. But they have clearly shown, given that M1 is different. And in the diagram, it's like that, but you can't just trust the diagram. Yeah, we take the forces of charges. Yeah, each charge separately. You mark the forces acting on each charge separately. This charge should be at rest. This charge should be at rest. So resultant must be 0. That's how you get the answer. You consider equilibrium. So here what I have done is considered equilibrium in this region. This is where I started, and then I manipulated those equations according to my requirement for equilibrium. Right, good. So the answer is third. A bit of maths involved, that you have to carefully do it. Not very difficult to understand, but we have done so many such questions in physics, past papers. Right, we'll move on to the next one now. Next question is third one. This is from the prototype paper. I think we have already discussed this. Give me a minute, I'll finish it quickly. Third one in the sense, the question from prototype paper, 2019 prototype paper, 25th MCQ. Which of the following statements is not true about electric field lines? Not true. Not true about electric field lines. We know a few things about electric field lines. They don't intersect each other. I lost my connection once again. Power cut. Right, okay. Can you see the screen? Hello? Is it visible? Right. Can someone just unmute and quickly confirm it? Can't read the texts.
Yes, sir, it's visible.
Right. Awesome. Thank you. Right, let's get back to the question once again. Which of the following statements is not true? So when you say not true, even though they have given it in bold letters, always just highlight it even more to make sure that you don't miss that out. Electric field lines always point from high electric potential to low electric potential. So it's going to be a plus and then minus. And even though we say plus minus, it doesn't mean this is positive and this is negative. Always this is taken as high potential and this is taken as low potential, and the electric field lines will be this way. So that is correct. This is how the electric field lines are. I think you should draw them parallelly. Yeah, that's okay. That's correct. This statement is correct, but they were looking for not true. Electric field lines are closer to each other where the electric field is stronger. That is also true. Let me explain that with another example for you. Now, if you take a point charge, let's say 2 point charges, plus Q and minus Q. And when we draw electric field lines, hope you can remember, we drew them like this. First we drew an electric field line from this to this, and then you draw it like this. Sorry, correct? You drew it like this. So these are the electric field lines. If you draw a small circle closer to the charge, and then on the other side, you know, the charge, the electric field lines, they go out like this, away from the positive charge, and they come towards the negative charge, something like this. So when you draw a circle closer to the charge, see, there are so many electric field lines in that particular region, so many electric field lines. If you draw the same circle away from the charge, yeah, there are only very limited number of electric field lines. Here there are 1, 2, 3, 4, 5, 6, 7, and here there is only 2. Electric field lines are stronger. Closer to the charge, electric field is stronger. So it's correct. Work has to be done externally in moving an electron along the direction of an electric field line. Right, we'll come back to that way. Electric field lines tend to attract one another. That is incorrect, no people. That is incorrect. Will they tend to attract one another? No, because electric field lines do not intersect each other. Electric field lines do not intersect each other. If they don't want to intersect each other, will they approach each other? They won't. So whenever they will always try to be away from each other. They will always try to be away from each other. So the fourth one is the incorrect one. That is wrong. But let's quickly check the other statements as well. This is wrong. Electric field lines are always perpendicular to equipotential surfaces. Yes, that we discussed. Hope you can remember. We discussed about equipotential surfaces. So in this case, if I draw equipotential surfaces, I have to draw them this way. Equipotential surfaces. Equipotential surface means a surface with points which have equal potential. Equipotential surface. An equipotential surface, equipotential surfaces and electric field lines will be always perpendicular. Yes, if I give you a quick example, one more example, think of a point charge plus Q. How do we draw the electric field lines around the point charge? They go away from the point charge like this. Wait, I'll complete it. These are the ones I'm drawing in, right? And can someone tell me how are the equipotential surfaces drawn? Can someone unmute and speak? The blue color ones are the electric field lines. How do we draw equipotential surfaces? Anyone? Come on. Did we learn equipotential surfaces we were at the class? Should have learned, no? Right. We learn, right? Yeah, okay. Equipotential surfaces must be perpendicular to these lines. So when you draw, let's say you want to draw perpendicular to this, yeah, it's not really a circle, it's a sphere, but it's okay. When you see from the side, it will look like a circle. So the perpendicular line to this is a line like this. One for perpendicular to this is this. Perpendicular to this is this. So when you connect all those perpendicular lines, what you get is a sphere. This is an equipotential surface. Around a point charge, it will be circles. Green color ones are the equipotential. Right, let's say they have given you a difficult task. They are asking to draw equipotential lines around these 2 point charges. You know how to draw electric field lines. Then what you will do is you will draw lines now. You draw a perpendicular line to this one, right? Perpendicular line, perpendicular line, perpendicular line, perpendicular line, perpendicular line, perpendicular, perpendicular, perpendicular. And then it's a matter of just connecting them, people, after that. Okay. I think when you connect those lines, dots, you get a You get something like this, don't you? So as you go further, it will be different. Now in the middle, everything will be like this. So in the middle, exactly in the middle, the equipotential line will be a straight line like this. Because what am I doing? For every electric field line, I'm drawing a perpendicular line. Then I'm connecting them all. And here it will be, in the other part, it will be something like this. Here it will be something like this. You draw perpendicular lines to each blue color line and then connect those dots. Understood? That is how you draw the equipotential lines. They will always work. And third one, we could not finish it. Third one, work has to be done externally in moving an electron along the direction of electric field line. So let's focus on the third one. First, let me create an electric field. Let me create an electric field. Yeah. So this is the electric field. Let me mark the direction of electric field. How should I mark the direction of electric field, people? From plus to minus, right? From plus to minus. So this is the direction of electric. Wait, I'll draw some lines first and then we'll put the arrow. Okay, this is the electric field, direction of electric field. Moving an electron along the direction of electric field means the electron is moved, electron has to be moved from here to here, right? Electron is a negative charge. Will it be easy for electron to move from there to there? Hurry up. No. Will it be easy? No, right? Why? Electron will be always repelled away from the negatively charged plate. You are trying to move the electron from here to here along the direction of electric field, movement of electron. Force is acting in the direction opposite, to the direction of movement. So here work cannot be done by the field. Field can't do the work. Field can only attract it towards the positive plate. If you have to take it from positive plate to negative plate, field will tell you, no, I can't do it. I can only attract it from negative to positive. You have to do it on your own. So we have to somehow make it go from here to here. So external work must be done. When do you have to do external work, people? When the force and direction of movement are opposite to each other. Okay. But if the direction of force and movement are in the same direction, work will be done by the field. We don't have to do anything. Is that understood? So that's why that statement is correct. If the direction of movement and the force are in the same direction, you don't have to do an external work. It will happen automatically. Work will be done by the field. Okay.